And I want to give one example, the typical STDP type example, because it's an easy experiment to do. So you can take a device and try this out. And we take the standard device, not the tungsten doped, for this particular measurement. And what we're doing is applying a pulse to the top and bottom electrode, separated in time by delta t. The potential difference between these is what we're calling the resultant waveform. And for these two with that time delay, it looks like this. And you'll notice you've got a 0 volt baseline here. So at some point you're going below 0, above 0, below 0 again. So if you've got a device that writes with a positive potential, erases with a negative, you're kind of giving it a little bit of whiplash because it's getting some negative, it's getting positive, it's getting negative again. What state does it end up in? It can be very confusing. So we investigated that, and we investigated 3 other pulse shapes, which at first glance you look at this and think they look fairly similar, but number 2, different from 1 with a little bit of a flat slope. Number 3 has a faster rise on that positive going portion, and I believe that's kind of a slower, gradual slope between the 2 positive and negative going peaks. And number 4 is just fast rising and fast slope. And we're looking at how does the device respond in terms of the percent weight change in conductance using this formula here, where R min is the minimum resistance we get to through the delta T test. So what's the minimum? That's just for basically giving everything a good baseline. So if we look at that, we can do delta T minimums from 50 nanoseconds all the way up to 50 milliseconds. So essentially a 1 second time range. And devices are responding as they normally do in an STDP type experiment. As you'd expect, delta T negative, it's erasing, delta T positive, it's writing, and so on. That all looks normal, it all looks really good. And if you change the pulse shapes, that previous data was for pulse shape 1, and that's this top one here. As you make it pulse shape 2, that has a flat top, you'll notice you're building in this region around delta T equals 0 that's flat and unresponsive, which is really important, because if you could do this and create a safety zone around delta T equals 0 with your pulses you're applying, that could be useful. Same thing with the lower slope. You get a nice flat region around delta T equals 0. Make a fast slope and you completely lose that. And you get a spike around that center. So that was pretty interesting. And then the important point for STDP isn't what those pulse shapes are necessarily as much as it is what the resultant waveform is across the device. How are you programming it really? It's really what is going across the device. So I'm going to show you just one quick example if you can see it. This is for pulse shape 2, the flat top there. You've got top electrode and bottom electrode pulses applied at some particular negative 40 millisecond delta T. Your resultant looks like this, and I've drawn 2 dotted lines. I think I lost me. Can you guys hear me again? Okay. I drew 2 dotted lines corresponding to the threshold for writing and erasing, and for this resultant, nothing goes above or below that threshold, so the device shouldn't really change. And as you change that to minus 20 milliseconds, you get a portion in red that goes below, so you should erase the device corresponding to that pulse width and that amplitude below. And as you increase your delta T, again, you get a positive going. So it really is about how much of the signal is above the threshold, how much is below, and what's your pulse width, what's your pulse amplitude. It's the same thing Professor Chua was describing in terms of the pulses being given to your device. It's not this one on the bottom, one on the top. Look at the pulse shape thing. It's what is the resultant across the device. And we've demonstrated that doing the STDP experiment and just putting resultants on gives the same result. It doesn't matter. And you'd expect that. You probably already know that.